This is the Insurance Institute for Business and Home Safety's Disaster Discussions podcast, where we explore the intersection of weather and the built environment. Welcome to Disaster Discussions. I'm your host, Rachel Penton-Goche. As wildfires grow more intense and frequent across California, a new frontier of fire science is emerging, one that looks beyond the trees and into homes. These burning homes located in the Wildland-Urban Interface produce a cocktail of highly toxic chemicals far beyond what natural biomass fires emit, spewing harmful compounds like heavy metals and volatile organic compounds into the air that residents breathe through contaminated ash and smoke, leaving residents susceptible to this air pollution as they begin the recovery process. In this episode of Disaster Discussions, we explore a research project led by UC Berkeley and funded by the California Air Resources Board aimed at understanding the emissions from burning structures in the WUI, where nearly 50 million Americans have made their homes. Today, we'll uncover how this work is reshaping our understanding of air pollution, public health, and climate resilience, with the scientists working to decode the emissions they produce. So joining us on the podcast today, we have a medley of guests, including Dr. Nathan Kreisberg, Senior Research Scientist for Aerosol Dynamics, Inc., and Principal Scientist on this project. We have Dr. Alan Goldstein, Professor for the Department of Civil and Environmental Engineering and the Department of Environmental Science, Policy, and Management, as well as Principal Investigator for this project, and Michael Milazzo, Graduate Student Researcher and PhD candidate, also with the Department of Civil and Environmental Engineering. So welcome to Disaster Discussions, everyone.
Thank you for having us.
Yeah, thank you very much. It's nice to be here.
And before we dive into our topic today, I want to take a moment to talk about some of the valuable public-private collaboration. We kind of have two collaborations going on here. Nathan, you are with Aerosol Dynamics. Alan, Michael, you guys are with UC Berkeley. You guys have your own collaboration going together. And then, of course, UC Berkeley is a valuable research partner of IBHS. So I'd love to hear about both of those partnerships and really the value that you guys see in both of those relationships.
Yeah, well, I think it's a great opportunity. It's a great example of private partner collaboration. Aerosol Dynamics is a small research company, and for years we've been collaborating with university groups to do research. It complements our technology and instrumentation development, and Berkeley is a great example. Alan's been working with my company for almost 20 years now, I think, over 20 years. And this project sort of exemplifies how the two complement each other. So we're developing technology with an aim to developing a new method of collecting and measuring particles, primarily is our focus. And Alan's group has developed over the years great insights into atmospheric chemistry, and that's his group's focus on the academic side. And so it takes really a combination of new measurement technologies and the insights and analysis to make use of what that technology brings. And so that's where the collaboration works so well. And this is an example where they're focused on measuring the emissions from fires, and we're helping them collect those samples, and the technology underlies it.
Yeah, and so in our 20 years of work together, we've developed quite a bit of instrumentation for looking at gas and particle composition, mainly the organic chemical composition, and we've done a lot of that through a variety of agencies like Department of Energy with a Small Business Innovative Research Program. We've also gotten funded by California Air Resources Board to do projects that are important for the state of California with respect to air pollution. And this is an excellent example of what we've been doing with IBHS. And in particular, the technological development for this project involved building a measurement package for the drone, and that required a lot of engineering talent and support. And it was a close partnership between Aerosol Dynamics and my group at UC Berkeley in order to do that. And it's been quite successful.
And before I get ahead of myself, I'd love to hear more about your backgrounds as well. If you guys could just kind of tell me a little bit about, your background, education, and how you came to work on this particular project.
My background is way back when in school, studying physics, and ended up merging into this nascent field of aerosol particle science, aerosol science, and it's only after many years of reluctant transition into airborne chemistry that some work got together with Alan's group and I started doing more of that. So my background is physics. We now doing more chemical analysis, but my company focuses on the physical properties of airborne particles. So this is counting and sizing the very small particles that remain airborne and can be inhaled and cause health effects. So my background is physics, and it sort of led me into the skills necessary to do some of the instrumentation development and electronics and mechanical engineering. But my role is largely of engineer with a science perspective to the collaboration. Yeah, we
have a lot of those at IBHS, so that fits in perfectly there. Alan, Michael, what about your backgrounds?
Well, so I was an undergraduate at University of California, Santa Cruz, and double majored in chemistry and in politics way back then. And then thinking about what I wanted to afterwards, I decided to focus on chemistry, but doing research in chemistry that focused on societal issues and problems that we could try to solve. And so I wanted to do things that were policy relevant. And I went to Harvard and got my PhD in chemistry there. And that's where I became an atmospheric chemist. And I started learning about the atmosphere and got much more into the organic chemistry of the atmosphere and really focused on emissions from different kinds of sources and their chemistry when these things were emitted. But then in 1995, I joined the University of California, Berkeley as an assistant professor. And I spent the last 30 years there running a research group where we've looked at all kinds of different emissions to the atmosphere, whether it's cars or from cities or from natural emissions from plants. And we've been doing a lot of instrument development over the years to try to enhance the range of things that we can measure. But wildfires became a much bigger topic in the last 10 or 15 years. There's been a lot of concern over air pollution from those wildfires. And in particular, the regulatory agencies have shockingly little information available about what was emitted from burning structures. So most of the work on biomass burning emissions had focused on the emissions from burning forests or shrublands or basically biomass. And we got into this project specifically so we could provide better information to the regulatory agencies and to the scientific community and to people who live downwind of fires so we could understand better what comes from burning structures.
Michael, how about you?
Yeah, so I got my undergraduate degree in environmental science, but I remember actually one of the first classes I took in college, there was a chemistry demonstration where they took a fish tank and then they put it inverted over some peeled orange slices. And they thought, nothing was going to happen. But by the end of the lecture, they flashed a laser through it, and you could actually see all this like cloud forming inside this fish tank. I thought it was just the craziest thing. And so that was kind of my first introduction into just the wealth of complexity that happens all the time around us in the atmosphere. So most of the time we don't see any of this gas that we're breathing in, but there's it's a very dynamic system. There's lots of things that are getting released into the atmosphere. There's lots of chemistry happening. And I took kind of that perspective into my master's of science in civil engineering. And that's kind of where I turbocharged this interest, where I started to understand that the organic gases and the organic particles that are in the atmosphere actually are a key component of driving some of both these health effects, but also kind of the chemistry happening. And so after working for some time, I was really interested in that as a topic, especially pertaining to fires, because they've really just become such a large component of what people experience as air pollution today.
Wow, I love that story about the fish tank. That is super interesting. Well, great. It's great to have you all on the podcast today. And I want to talk about your research project you've all been involved with at IBHS. So just kind of getting into it, wildfires, as you guys have all mentioned, they're increasingly consuming homes and communities. And for these conflagration events, we've seen the Camp Fire, the Lahaina Fire, and of course, the beginning of this year, the LA fires. Structure fires in the WUI transition to urban fires as they consume our homes and the objects inside them, and they remain a growing concern as they become more frequent and more severe. So, Alan, you hit it on a little bit, but I'd love to hear all of your perspectives on really, more on what inspired this research into structure fire emissions and why now? Is it because they have become increasingly severe and really prevalent events in our society? Just talk a little bit more about the inspiration for this project.
Yeah, so our field has, with the research that Alan's mentioned, our field has really explored the emissions from burning plants and trees, which we call biomass burning. We've been researching that for decades at this point, and we have a pretty good understanding of the complexity of the different types of chemicals that get emitted, as well as the implications for the air quality near the fire and also downwind. There's still a lot of unknowns there, but by comparison, when we start burning homes or vehicles or other materials that are not found in biomass, we really don't know what's in it. So there's really not almost any research by comparison to the biomass burning field that have characterized the emissions that are coming off of these types of events.
Yeah, if I'm a person living in or near the WUI, I would certainly be concerned as to, what is in the smoke when these wildfire events happen, what is in the water, what is in the soil. So this sounds like very valuable research that you guys are doing.
Yeah, and especially as the wildfire intensities have increased, and here in California, it's a major concern. The progression of people living more and more in these environments are adding the structures that are unique, the fuels as we refer to them, but the intensity of the fires in turn, because of longstanding forest management practices and climate change, are leading to higher intensity and fires that are less able to be controlled and contained, and so they're causing much greater consumption of homes. Unfortunately, they're at the boundary, and so the contribution of these emissions from these kinds of structures is now starting to rise to the point where, even on a broader regional and climate level, needs to be determined.
I would just add to that one of the concerns, of course, is first responders who come in and try to fight the fires are being exposed to high concentrations of emissions from the structures that they're trying to save. And there's not been enough information available to understand what they're really exposed to. And so we want our work to be able to contribute to a better understanding for people who are exposed, whether it's residents or first responders or people that are living just downwind of where the fires are.
Earlier this year, we had the Palisades and Eaton fires. That was about 16,000 structures that burned in the span of a day or two. How has this more recent event highlighted really how urgent this research is for you guys?
It's a urgent and ever growing problem that we're observing these mass urban fire events that have really started to happen in the last 10 or 20 years, really. And as we continue to develop within the Wildland-Urban Interface, we start to build out more. We encroach on these natural landscapes that are burning with increasing intensity and frequency. There's just more houses that are being exposed to this type of risk. So we're kind of in a new regime, it seems, for a heightened amount of risk for homes at these interfaces.
So I want to talk more about why this is so problematic. You guys have mentioned when homes burn, they release more than just smoke, things that you can't see. Like Michael mentioned, they emit a cocktail of toxic chemicals, plastics, metals, synthetic, petroleum-based materials, and structure fire emissions pose a range of environmental and health risks that current models fall short in accurately capturing. So first, I want to start with the term EF, or emission factors. Can you just kind of explain this in layman's terms? What does that mean?
Sure. Well, an emission factor is that if you burn a certain submaterial, there's going to be gases and particles that are emitted when you burn it. So the emission factor is basically looking at the fraction of the burned material that gets released as a certain chemical. So it would be something like the micrograms of particulate matter per kilogram of material burned, something like that. So it's a way to scale from a massive structure to what you'd expect to have emitted into the atmosphere. And that can be very useful when you're trying to understand the total emissions from burning structures or from burning thousands of structures. It's a way to scale up, get a handle on the massive emissions that are actually there, and then put that into air quality models to try and track where the pollution is going.
Fortified Fred here. At IBHS, we've spent more than a decade studying the damage caused by hurricanes, tornadoes, high winds, and hail. We identified the common weaknesses in homes built using conventional construction standards and spent years researching the best solutions by putting them to the test at our research center. Now, you can use our science to defend your home or business simply by asking your builder or contractor to follow the Fortified Construction Standard to protect your home when severe weather strikes, keeping the roof on and the rain out. Visit fortifiedhome.org to learn more.
IBHS, of course, in partnership with CAL FIRE and others, have been conducting the wind-driven building-to-building fire spread experiment over the last couple of years. Phase 1, we looked at the spread of fire between a shed and a target building. Phase 2 looked at the spread of fire between an accessory dwelling unit or an ADU and a target building. So Nathan, Michael, you guys joined us on the IBHS campus for Phase 2, measuring those emissions from those controlled burns. Full-scale buildings filled with realistic fuel loads, furniture, appliances, household accessories, even clothes hanging in the closet. All of it was set on fire for this project. So your involvement in this project, as you guys alluded to earlier, involves some drone work. The Firehawk UAV. This was custom built for this project. Nathan, I think this is in your realm. Tell me a little bit about the Firehawk. How is it used to collect those air samples during these burns, and kind of explain what it is you did during the burns?
Sure. Maybe I'll take a step back and talk about the evolution from prior projects, because most of our work, both Alan's group and what we do is usually stationary sampling or maybe certainly terrestrial-based sampling, except for perhaps from a tower or an airplane. But when we took on the task of trying to take some representative samples from a prescribed fire up in the Sierra foothills. So we had a project where prescribed fires were going on. There was no one collecting smoke and gas emissions. And so it was an opportunity to do some sampling. It was pretty clear from the beginning that just sampling from the ground was going to be a limitation. So we looked into developing a drone-based collection approach. This was new to us, so we first purchased a large drones, DJI 600 Pro, for those who are familiar with drones. And it's able to lift fairly large payloads, which we needed, up to 10 pounds, and safely fly in highly turbulent air masses, which is what you see with fire plumes. So we quickly studied up on drone piloting. I went to drone camp with Alan's postdoctoral researcher at the time, and the two of us got certified, got our pilot's license. It was all new to me at the time. This is around 2017. And I'll tell a little funny aside, we knew we were going to sample from the drone, but we didn't have anything sort of on the shelf, or we had never done this before. So we reached out and we identified a company in Canada that sold the package that was suitable. It does real-time gas measurements and radioed the measurements down to the ground, so you can monitor during the flight what the conditions were. And this seemed great. It was attached to the drone well, and we flew it, and it was going to be no problem. But weeks before the deployment, just sitting on the bench in the lab, it started to smoke and nearly burst into flame. So we weren't able to resolve it, and we basically had to set it aside and quickly, in about 3 weeks, put together a much cruder package to do that sampling. But it worked, and we collected their samples. And then during the follow-up study a year later, we developed our own package from the ground up. And that involved developing both the control system and something tailored to what we needed. So the advantage of building it yourself is you get exactly what you want. And so through two design versions, we developed first a single sample-based drone package, which we deployed in those prescribed fires. But then when this project came along, it was a little different. With the fires, prescribed fires, the forest burns. There's a lot of it all day. And so the timing is very different. You've got the luxury of collecting samples over a long period. And so each flight, you'd only collect one sample, and that was just fine. But here, with the structure fires, you can imagine once it goes, and it's burning on its own terms. And within an hour, there's nothing left. So we were faced with the decision, and we were going to take one long sample and hope that it was representative, or could we manage to collect multiple samples during the course of the burn and therefore have some replication, which is always reassuring and useful if it evolves over time. So that's what we did. We designed a box that had 3 channels that could measure sequentially particles and gases. It had real-time sensors for carbon dioxide and carbon monoxide, which are the 2 main emissions from the fires. And that information from the gas sensors was transmitted down to the ground by non-interfering radio signal, very important, not to interfere with the drone communications. And from there, we could determine, crucially, whether or not you're in the smoke plume. Because one of the restrictions for drone flying is you have to maintain line of sight at all times. And so the drone has to be between you and the obscuring smoke plume. But it's a little hard to tell whether you're actually in the plume or not. So this is where the real-time sensors tell you CO2 is elevated. We now know we're collecting sample. And so we designed it so that you could monitor that accumulated signal of the CO2 and decide when to switch to the next sample. And so we would collect 3 samples per flight and then bring the drone back and replace its batteries. And we had 2 boxes, sample boxes. We'd swap one out and then resume the fight to try to collect as much as you could. And that's how we collected the samples. And it remains to be seen through the analysis how successful we were with replication. So that's where the details of what was burning and how over time, some of those details, you have to dig into the data to see were we replicating or are we tracking something that's evolving over time.
Yeah, I know you guys had some logistics. You had to get all the way from the West Coast to the East Coast. The burn, whether or not the burns happen is a very specific process. We have specific weather conditions that are needed, from the wind to the temperature to the relative humidity. And then of course, even as you guys know, on the day of the burn, sometimes, those conditions weren't just right. So very, very particular conditions needed. You guys did a great job with really kind of handling those logistics of getting to and from the burns from coast to coast. Talk about some of the challenges that you face when collecting those samples during the active burns. Just to put this in perspective for people who have not seen the experiment, being up close to a wind-driven fire with winds as high as 55 miles per hour is no easy task. It's a very volatile environment. There's a lot happening on campus as these burns are happening. So I imagine, you guys handling a drone and the samples, maybe some challenges. Can you talk about that aspect?
Well, certainly the timing was challenging. The weather conditions had to be right. We're on the West Coast, and this is the IBHS is on the East Coast, Southeast. So it meant planning and trying to take our best guess as to when we would arrive. Preparations were tried to keep to a minimum so we could arrive, a day ahead and do the prep necessary and be ready for the burn if it was called. In one case, it was, canceled and we had to come back the next week. That only happened once in 8 tries. So that's 8 different burns. So that wasn't too bad. As far as planning for the day, you just have to be ready, because when they light the match, you got to go. So you have to be sure all the batteries. We swap out. We have 3 sets of batteries for the drone, so they're all charged and you're prepared to swap those out. We have the 2 sample boxes prepped with their sample collectors, and so you can, with pretty quick turnaround, collect back-to-back samples. The actual sampling from the drone with the wind, you basically have to, the higher the winds that they apply with the turbines at IBHS, the further back you'd have to be or further away, just because you rely a lot on the ability of the drone itself to remain stable. And so it naturally is designed to hold a position. It has redundant GPS, and it's quite sophisticated in that regard. So we've never lost a drone flying. The only issues we've ever had have been on the ground. So once you can get up into the plume, then it's just a question of trying to gauge where you are and at what point do you want to take a break. It's sort of like NASCAR. When do you take that pit stop? We don't want to miss anything. So we try to get samples first of the background before they light anything. You want to make sure that the vehicles that are on site aren't active. So we wait for the Pittsburgh Fire Department to arrive and turn off their diesel engine, so we don't want to sample that. We can get a clean background, and then when they light the structure, there's the starter. Like any fire, you often use a different material to get the fire going. We're not really interested in that, so we don't want to collect the first sample that includes the crib, which is a stack of wood, or certainly any accelerant. And a couple of them, they had to use some actual fuel. So you wait until that's sort of burned up, and now you're just sampling. You want to sample just the burning structure itself. And there are various phases of the burn, and you try to capture those different phases. There's what's called the flashover, when suddenly the whole building becomes engulfed, and the walls have been penetrated, and you've got a lot more ventilation going on. And so we'd like to get samples before and after that. And then once it's all died down and just sort of smoldering, we try to get samples of that state as well.
And before we do any suppression on what is left of the fire as well, right?
That's right. Yeah, we ask them to hold off on the water hoses, so we can, So it does extend the whole operation a little, but the team at IBHS was very accommodating. And even though what we were doing was unrelated to the fire science questions that they were trying to answer, it was a good collaboration. We felt very well supported.
And you mentioned flashover there. That's a great segue to what I wanted to talk about next. We're going to talk about, some of the additional compounds that are in the smoke, but I want to talk about the different burning conditions as well that you mentioned affect the chemical makeup of the emission. So oxygen star fires to those high heat flashovers, very complex. So in real WUI fires, the fire spread occurs rapidly and can cause something called non-ideal burning conditions. Can one of you explain what that means?
The combustion state directly drives the type of emissions, and we see this both in controlled combustion experiments in a lab, where you might have just a single fuel, a log being burned, and we've done this sort of work trying to characterize emissions from different biomass materials, and whether it's actively flaming or not can determine directly what kinds of emissions you get. So there's a parameter called modified combustion efficiency, which is a fancy way of just saying, how efficient is the combustion, how much oxygen is present, do you get good combustion or not? And we actually measure that indirectly by the amount of carbon dioxide that's present. So the less efficient, the more smoldering state, you'll get an elevated carbon monoxide emission along with the carbon dioxide, the CO2. And so looking at the ratio of those two, essentially you can tell whether it's flaming or smoldering state. And so we try to characterize the emissions collected by that parameter. How close to full efficient combustion do you have? And as it relates to the structure itself, what we're seeing, not to get ahead of ourselves on actual results, but the burns are quite efficient, and so we see very little smoldering state signature in the data, and it's very highly efficient, unlike what we saw in the wildfires. So the fact that you have so much essentially dry tinder present in the structure, by design, of course, it's designed to stay dry. It burns very efficiently, unlike in a forest, it's largely made of living green material. And tends to smolder much more prevalently.
So tell me about some of the different samples you collected during the experience. You mentioned carbon monoxide, carbon dioxide were the main ones, but I know you're actually looking at these different harmful or hazardous emissions. Some of the things mentioned in your proposal that you sent me, things like metals and VOCs. Talk about that. What are some of the other types of things that you detected in this smoke?
So with these types of ADU combustion experiments, you really only get one shot to capture the smoke. If you miss your chance, the building will continue to burn. So we wanted to be as comprehensive as possible with our samples. So we took, as Nathan had mentioned, kind of real-time carbon dioxide, carbon monoxide, and that helps us both inform whether we're inside the smoke plume, so we can actually be confident that we're actually sampling smoke, as well as kind of, as Nathan was also saying, contextualizing our results, whether there's a bunch of carbon monoxide that might say that it's burning really inefficiently at that time, or it's mostly carbon dioxide, and so it's actually burning more efficiently. The samples that we also took on our fire package, we took a series of 3 different samples for each flight. So we took sorbent tube samples for analysis of the organic gases called volatile organic carbon. We also took 2 particulate samples on filters, and those were used to both do just the total PM 2.5 mass, that's particles less than 2.5 micrometers in diameter. And then, now that we have the total mass of the PM 2.5, we can start looking at the chemical makeup of that. So we looked at both kind of the elemental carbon, or kind of the soot, as well as the organic carbon content. And then we looked for wide range of inorganic elements that we're able to find, trace amounts of in the smoke. And so all of these samples were collected in real time, but then taken down to the ground, and we actually shipped them off for analysis.
We can't stop wildfire, but there is a pathway to better protect your home. I'm Steve Hawk, Senior Director for Wildfire at IBHS. If you live in areas at risk of wildfire, consider building or retrofitting your home using our Wildfire Prepared Home Standard. It addresses ways you can make your home more resilient to wildfire by creating a 5-foot non-combustible zone and preparing your home's exterior to help break the pathways of fire spread. Visit wildfireprepared.org to learn how to protect your home and apply for a Wildfire Prepared Home designation.
I'll say we're actively working on making some very interesting results, and the preliminary results we've seen so far are really exciting. I will be presenting some of this work at a conference pretty soon, and then hopefully in the months that follow, we'll be submitting a paper for publication on more of the bulk properties of some of the smoke, and with a follow-up paper sometime next year of kind of the individual chemicals, and that really should inform how toxic this smoke is compared to other types of smoke from wildfires.
I'll just add that as part of our contract with the California Air Resources Board, we're required to do a final report that will report all the data and provide all the data to them, and that report will actually become publicly available. And I think we'll probably finish that report in approximately 1 year from now.
We can't really say anything specifically yet about the toxicity from those types of materials, just because we don't have the results from our work quite ready yet. But I will say that there's a National Academies report in 2022 that was published on the chemistry of fires at the Wildland-Urban Interface. And they have some really interesting results in there that show for a structure, most of the mass is actually still lumber. So it's actually biomass. Now this lumber's been treated, so there's slightly different properties to it, and there's kind of chemical additives. But if you were to burn an entire structure, most of the mass that's been consumed is actually lumber. So we're seeing some results that are similar to biomass burning emissions. But as Alan kind of just mentioned earlier, this emission factor to kind of normalize our results by how much mass was consumed, those types of emission factors are vastly different between a lumber or a plastic or a shingle. So while a roof shingle may only be, or I should say, so while the roof may only be a couple % of the total mass of the structure, it actually might be disproportionately producing more toxic chemicals in the smoke than the lumber is. So that's kind of where these this unique complexity of urban fires comes into play. We don't really know how these really small components of the structure scale up to be major contributors to toxicity.
Yeah, that's really interesting. Just one thing that comes to mind is, when you look at your furniture and you see all the warning labels and all the different chemicals and toxic materials that, even your couch could be made of, everything says highly flammable on it. So, and just hearing anecdotal kind of comments from some of the firefighters in California and when we were there for a survey about how much hotter fires burn, not only in these situations, but in the modern age with our modern furnishings and the things that are in our homes made from these man-made materials.
I'll add that I'm excited to be able to provide to the regulatory agencies, specifically the California Resources Board, but I think the U.S. Environmental Protection Agency will be very interested in this too. The actual chemical composition amount of emissions that you get from burning structures. And they'll be able to use that in air quality modeling. They'll be able to use it in risk assessment for first responders, for people that live downwind, and to also understand better if there are chemical markers that we can observe that are specific to some of the materials that are in structures to help us understand what burned when we're looking at the smoke downwind.
I have one final thing to add of just the type of research that our field conducts to understand the emissions is either kind of looking at the smoke in the real world when one of these events happens and trying to capture the ambient smoke in the air, or really the absolute opposite side of that is burning individual materials in a very controlled laboratory setting. But comparing those two methods is really difficult. There's a lot of extra variables that happen in between kind of a controlled lab situation and a real WUI fire. And so that actually points to how unique and powerful these experiments and this collaboration was with IBHS, that to date, to our understanding, there's no comparison to the scale of event, or the scale of experiment. So we really should be filling a major gap in our understanding of how emissions from these types of events happen at a much larger scale than we've ever been able to test before.
All right. So the last thing I wanted to ask you is, how does this work on air quality? How will that complement some maybe other research that's going on? I know there are questions being asked about, what is the soil quality and what is the water quality after these major conflagration events? How do you guys hope to contribute to better understanding, what the environment is where these people live after these large scale events?
Well, I'll make one comment on that. There's been a lot of work, particularly out in the Western United States, at reducing air pollution, and California has had a major focus on this. But it's true across the country that air pollution is much lower than it was in the 1970s and 80s. And when we look at current air quality regulation, one of the things that is the biggest problem is PM 2.5. And in the Western United States now, if you look at exceedances for PM 2.5, it's almost all due to wildfires at this point, at least in the San Francisco Bay Area, but through much of the Western U.S. And so understanding the emissions from these wildfires and the contribution from structures within the Wildland-Urban Interface is really important for solving what is today one of our biggest air pollution problems. And I think that the public will be very interested in these results, as will the regulatory agencies. And some of that particulate matter and other chemicals does get into soil, it gets into water. And so it's many of the same chemicals actually that are emitted into the air as get into the water and soil that can linger and have a longer term effect. The air is actually transported away fairly quickly. So within a few days, the smoke typically clears from an area after a fire, but the residual that's left in the soil, that's left in the water, persists for much longer. Thank you very much for interviewing us, and best of luck with putting together your podcast.
This has been Burning Questions, uncovering what structure fires are telling us about air quality. Partners in Resilience, Part 2. Thanks for listening to the Disaster Discussions podcast. Join us next month for a new episode. For more on IBHS's ongoing research efforts, visit ibhs.org.